That's right, you weren't here. I asked if people were gone on Friday. All right, so please start. Uh, take all your worksheet from Friday, and we're going to look to the back side of this worksheet. And today, so on Friday, we learned how to do right-hand sum, left-hand sum, trapezoidal sum, midpoint sum. We learned how to do it all by hand. Today, what we're going to do is we're going to use our calculator. Okay? And then I'm also going to teach you how to add up the area of an infinite number of rectangles. So we've got a lot to do and not a lot of time to do it in. So let's try to get through an example, give you a little bit of time to work, and then we'll move on from there. So this function negative x squared plus 16 looks like this. And it says that it's bounded by the x-axis, the y-axis, and it says I'm going to construct 16 rectangles, and I'm going to find the right-hand, left-hand, midpoint, trapezoidal sums. Okay. So for everything, we take the width times the sum of the heights. That's what we've been doing the whole time. Find the width of the rectangles, and then we add up the heights. That's it. So for right-hand sum, anybody tell me what the width is of each rectangle? A fourth. How do you get that? 4 minus 0, so that's the length of the interval, 4. And then you divide it by the number of rectangles, which was 16. So 4 over 16, or I'm sorry, 1/4, right, is 0.25, times the sum of the sequence of, what do I type in next on my calculator? The function negative x squared plus 16. I define my variables x. So look at this rectangle right here, okay? So my first interval is from 0 to 0.25. If you're doing the right-hand sum, are you going to evaluate the height at 0 or at 0.25? So you enter 0.25 as your beginning spot, which you're going to evaluate it. What's the last spot? So my last interval is from 3.75 to 4, and the right side of that interval would be 4. And then what's the width of each rectangle? 0.25. So we go 0.25 times the sum. So I go to second catalog, grab S, or actually I could grab T for sum. Go up. And then catalog S for sequence. And then negative x squared plus 16, comma, x, comma, 0.25, comma 4, comma 0.25, double parenthesis, enter, 40.625. Can you tell if that's an overestimation or an underestimation? It's an underestimation. Yeah. Because we're doing the right hand sum. And as you look at this rectangle, what's the right hand side of that interval? 0 or 0.25? So we'll move to the right hand side. For the left hand side, 0.25 times the sum of the sequence of negative x squared plus 16, comma x. So now what's the left hand side of the first interval? 0, 3.75, and what's my width each time? 0.25. And so what you can do is on your calculator, you can take second entry and it'll bring that back. And so all you have to type in then is 0, comma, 3.75, comma, 0.25, 44.625. Will that be an under and over? Over. And your midpoint sum. So look at the middle. What's the middle of 0.25? 0.125. So bring my entry back. I'm going to start at not 0, but at 0.125. What's going to be the last spot? 0.125 back from 4. So 3.875 and 0.25 is still my width. And 42.6875. I should have written this down. How do I figure out trapezoidal sum? Yeah, so 40.625 plus 44.625. You add them up and you divide them by 2 to average up 42.625. Right. Trapezoidal sum is the right-hand sum. 40.625 plus 44.625. Divide by 2 to get 42.625. Would that be an overestimation or an underestimation? We do. Watch, if you draw a rectangle like this, okay, and remember, you would draw the trapezoid like that, and so you can see it's an underestimation. It's concave down, so it's not an underestimation for trapezoidal sum. So you should be able to do that. Now, let's find the exact. And the way you find the exact right now, because you don't know the calculus set, which we'll teach you in a second. So you type your function into there. And then I go second calculate. Which one do I grab? 7. Lower limit of 0, upper limit of 4. And you can see that it gives us 42 2/3. So, you know, we're pretty close with that. Is that good? Everybody got that? Okay, I'm going to give you 3 minutes to work on, you know, try to get another one set up, and then we got to get in the rest of the notes, otherwise we won't finish before the bell. So go ahead, we'll pause, and get back to this in a second. Okay, so there's a few people that have missed today, and today's not a good day to miss. There's not really any good days in calculus to miss moving forward. What we want to do is, starting 5.2, we want to look at the definite integral as a limit of Riemann sums. And so we're going to teach you about that today. Again, we are starting integral calculus, which involves the rectangle piece, you know, just adding up these areas. And remember from my song I wrote you, remember I said the word infinitesimal? Yeah, so that's where the word calculus comes from. The ability to calculate the infinitesimal. So something infinitely small. For example, when we found the slope between 2 points, we made the distance between the 2 points go to 0, yeah, infinitely small. And right now, since we're going to draw an infinite number of rectangles, the width of each rectangle is going to go towards 0. It's going to be infinitely small. And so being able to calculate that is the whole idea of calculus. That's what it means. We're going to calculate the infinitesimal. Okay, so what we want to do is we want to find the exact area bounded beneath the curve x squared from 0 to 2. That's our goal. And what we're going to do is we're going to start off by doing a basic example just using 4 rectangles. This picture is not the picture we're going to use. All we're going to do is draw the real picture, and then you guys will break for lunch. You guys know the picture looks something like this, right? Go grab some lunch, and we'll do it when we get back. Okay, I hope you had a good lunch. We come back here, evaluate the right-hand sum using 4 rectangles. So I'm going to take the width times the sum of the heights. If I divide this up into 4, what's the width of each rectangle going to be? A half. And it's going to be a half. And here's how you got that, if you don't realize what you did. You took 2, which was the ending point, minus the beginning point, and then you divided it by the number of rectangles. So that's what you did, okay? So now I'm going to add up the heights. Where will I evaluate each one of these heights? Where do I evaluate the first height? I evaluate at a half. So I have 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared. Are we okay with that? So that's going to give me the right-hand sum, okay? So that's what we've been doing. What I want to do is I want to take that, and I want to move that instead of adding up 4 rectangles, all I want to change is I want to add up an infinite number, okay? So it's no big deal. And these first two, there's really 3 big pieces to this problem, okay? And this is not easy. This is, a lot of times people leave class after they're like, I don't think I could ever do that. They come back tomorrow, they're like, hey, I think I kind of get this. And then, 2 days later, they're like, yeah, I could definitely do that, okay? So we're going to get you to that point. But you need to understand really 3 big pieces. And the first 2 big pieces are right here. First one's not that bad. The second one's more challenging for people, okay? So I do my absolute best to explain. So I'm doing my best, so please do your absolute best to follow along and take this in. The question is, if I have 4 rectangles, the width was 1/2. The question is, what's the width of n rectangles? Yes, Kimball, how did you get 2 divided by n? Yeah, so he took the ending minus the beginning divided by the number of rectangles, or b minus a over n. So he said, let's take 2 minus 0 and divide it by the number of rectangles. So the width of each one is 2 over n. Remember that? Okay. Any questions on that? The width is very important. If you think about it, all I need is the width times the sum of the height. So we've got the width. Sum is just adding. So now we just have to figure out the heights. Well, we just squared these values, right? So the question is, what values do we square? For what x values do we evaluate the sum? We chose 1/2, 1, 3/2, and 2. Tell me how he came up with those so we can write an expression. Okay, so we added what to itself? I need more description. Okay, forget about the 2 over n piece right here. Just describe to me how we came up with those. Okay, so we went over the width each time from the beginning, correct? So we took the beginning spot, which was, and we went over 1 width. Then we took the beginning and we went over 2 widths. Then we took the beginning and we went over 3 widths. And then we took the beginning and went over 4 widths. My goodness. Okay now? All right, great. All right, so 4 widths. So watch what's happening here, okay? For what x values do we evaluate the sum? You took the beginning and you added a certain number of widths. Now, I is just your rectangle number. I is just your rectangle number. So look at this picture here, okay? We've got these four rectangles. I equals 1, I equals 2, I equals 3, I equals 4, or intervals, okay? For the first, to get to the first spot, to get to x sub 1, we take the beginning, which is x sub 0, and we add how many widths? 1 width, which is what I is. Then we add 2 widths from the beginning, and then we add 3 widths from the beginning. See that? So why this I piece? Well, look it up there. See how we sum from I to n? So that's how we're going to use that. So in this situation, what's our beginning? Where did we start? 0. So we have 0 plus I times, and we already know what b minus a over n is. It's 2 over n. So we get 2I over n is, that's the spot where you evaluate the x values. Escape. Click on. First, we're going to express the area as a definite integral and as a limit of an infinite Riemann sum. So now we're going to connect this together. You say that to a mathematician, and they're going to be like, oh, wow, you really are intelligent if you know how to express this definite integral as a limit of Riemann sum. So this is a definite integral symbol, or an integral symbol. We'll talk about definite and indefinite at a different time. That means basically the sum of the heights, okay? What are the boundaries that we're using for this problem? 0 to 2, okay? And we're going to sum up the heights. We're going to plug these x values into what? Into our function, right? Into x squared. So that will sum up those heights, and we got to multiply by the width. And the width, we use this representation of dx. Okay? So you can see it up there on the board, what I have. I have the whole thing written out. So in this problem, we're going to write is equal to the limit as n goes to infinity of the sum from the first rectangle, or the first interval. We're going to move it to n rectangles. See what this is? Sum, okay? And you see n is being pushed to infinity. So we just throw that limit in front of it so we can go to infinity. So we're going to sum, and we have to, you can see it says f of x sub I. Do you see that? X sub I is the spot where we evaluate the heights. Okay? That's where we evaluate the heights. So we have to take that x sub I, which is this guy, and we got to plug it into the function. What happens if you take 2I over n and plug it into the function? I'll just write like this, 2I over n quantity squared. We'll deal with it later. And then you see that last piece, after f of x sub I, you see that delta x, triangle. That's a capital delta in Greek. So dx and delta x are going to be interchangeable, basically. So then we attach the width onto this, and the width is 2 over n. Do you understand what we just did? Okay. Let's try to just push through it one more time. Taylor, I'm going to explain to you, and you tell me if I lose you along the way, okay? First of all, look at this. This is just what we're trying to do right here. We're trying to add up the area from 0 to 2. That's what that is. In order to do that, we are going to sum the heights. You chose to evaluate at 1/2, 1 and 3/2, and 2, and you plugged all those in and you squared them, right? Well, instead of writing that, we would have to write an infinite number of those. I can't do that. So I wrote an expression, 2i over n is what those pieces are. And I plug that in and I square it. See how I got this width here, 1/2? I've got my width of 2 over n. Instead of writing all these pluses, I have this sum sign. And I'm going to sum from 1 to n, and we're going to push n to an infinity, so that way we have an infinite number of rectangles. What is n? N's the number of rectangles. How many would you like to do? 7? That's boring. I can do that in my sleep. I want to do an infinite number. Okay? So, no, I is the spot, is the rectangle number. So this is your first rectangle, second rectangle, third rectangle, fourth rectangle. In order to get the height, you take 2i over n and you square it. That will give you the height. I and n are very, very closely related. They're very closely related. But it's not the same. We use I for really counting purposes. Okay? So you'll see what happens to the I and the n. Because we do use the I to get some n's from it. Okay? So, all right. So this is equal to the limit as n goes to infinity of the sum from I equals 1 to n of 2i squared over n, 4i squared over n times 2 over n. Are we okay with what I wrote down there? Two squared is 4 times 2 is 8. Are we okay with that expression? Okay, now to get back to Bo's question, I and n. Bo, I becomes n. N is the last number. But I start with 1, and then 2, and then 3. I end at n. I end there. Okay? So, now, if you look at this expression, okay, it says we are going to take the limit as n goes to infinity. Do you know how to take limits as n goes to infinity? We've done that, haven't we? So if I could get rid of this I piece here and just have n's, that would be a nice thing, wouldn't it? So what I'm going to do is I'm going to factor something out so that I have an expression with just i's. Watch what I do. I have the limit as n goes to infinity of 8 over n to the third times the sum from I equals 1 to n of I squared. See if you can wrap your brain around that. See what I did? What? This sum. Sigma notation means sum, means I'm going to add up a bunch of stuff. So instead of writing all these plus symbols that you see over here, all I have to do is just write sum and it adds it up. We did it last year, so I'm sure you remember it very well. You had a wonderful college algebra teacher. All right, here we go. So now, see how I factor that out? Now I've got n's, but I've got this I piece right here, okay? All right, time to digress just a little bit so you understand what to do with that. I want to get rid of the thing right here. I want to get rid of that, okay? Don't write this down. I'm going to show you how we got rid of it. Remember last year we did something called math induction? remember uh, Gauss was in school and teacher, he misbehaved and teacher said you got to stay after school till you add up the numbers 1 through 100, and he found that it was 5,050 because he took 1 plus 100 was 101, and then 2 plus 99, 3 plus 98, they all had 101, right? Now how many pairs are you going to have? 50 of them. So he said it's 5,050, duh. Right? So, so basically what he said is if you sum from I equals 1 to, instead of 100, let's go to n, what you do is you take n times n plus 1 and you divide by 2. Whoop, should write an equal sign in there. So if you add up those numbers, you get n times n plus 1 divided by 2. And we proved that a lot of those things were true. Remember spending some time in mathematical induction doing that? You show it was true for case 1, and then you assume true for case n, and then you show true for n plus 1. So it was the next term. Well, we showed that that was true using math induction. I also showed another one. That's very similar to what I have written on the board, isn't it? I mean, the only difference is that one has a squared on it, doesn't it? Well, we also showed this one last year, and second hour said that they would like to see this done just one more time. So tomorrow, open class, where I'll do a math induction problem so you can trust. Well, we've proven all these to be true, and you may not remember, but we did it. And we said that if you add up the squares, so like 4 or 1 plus 4 plus 9 plus 16, so on and so forth, that adds to n times 2n plus 1 times n plus 1 divided by 6. So I can take this piece and replace it with that. Remember, our goal is to take what you have sitting right here and write it so that there's no more i's, so that there's just n's. So here we go. Limit as n goes to infinity of 8 over n to the third times, and instead of that piece, I write the known sum. We know what that adds up to. It adds up to n times 2n plus 1 times n plus 1 all over 6. My new limit has only n's, doesn't it? What? Oh, okay. All right. Glad we got through that. You just you just do whatever you want, Sini. Crown her queen, and she thinks she can do whatever she wants. Unbelievable. All right, here you go. Limit as n goes to infinity. We're going to FOIL this out. 2n times n. Very good. Times n, 2n to the third. Then I got 2n times 1 and 1 times n will give me, come on people, we're foiling algebra. 2n times 1 and then n times 1. 3n times n is 3n squared. 1 times n all over 6. No, don't cross multiply. Limit as n goes to infinity of 16 n to the third plus 24 n squared plus 8n over 6n cubed. Remember how we evaluate that limit? Factor out what? Largest power. Limit as n goes to infinity of n to the third times 16 plus what? 24 over n, 8 over n squared, all over 6 into the third. What happens? 0, 0. Whoop. 16 over 6, which reduces to okay, I heard Bo say this. He says, I want to check it. Let's check it. Go x squared. You make the graph, and Bo's going to check. He's going to go second calculate, number 7. And he's going to go from 0 to 2. And so we did just add the area of an infinite number of rectangles. We came up the left-hand sum, right-hand sum, midpoint sum, trapezoidal sum, those are all estimates. We have used the limit of Riemann sums in order to come up with the exact. Right, so the next couple days you will spend time finding the exact area using this limit. No, I would like to quiz you guys over left hand, right hand, trapezoidal sum, midpoint sum. Yes. So what Kimball is holding up is homework. That's what I gave to you guys. No, no. We will continue on this tomorrow.